Right. Our next speaker is Léo Colisson, who's going to talk about classical client blind quantum computing.
Thanks. So I will present today our work on classical blind quantum computing, which is a joint work with Alexandru Cojocaru, Elham Kashefi, and Petros Walden. So you may know this famous story about Robin Hood, this guy that tries to help poor and weak people by stealing from rich, powerful, and mean kings. So in the next 15 minutes, we are going to be Robin Hood together. So let me present first to you Alice. She's the girl we want to help. She only has a classical computer and a cup of tea. On the other side, you have Bob. He is very powerful and has a full quantum computer. It appears that Alice would like to perform some quantum computation. She would like, say, to factorize a given number using the Shor algorithm. One naive way to proceed would be to simply send the computation as input to Bob, and then wait for the result. The thing that we would like to hide everything to Bob, because Alice may want to perform some secret operations, so we would like to have a blind Bob. So we cannot use this method anymore, so what we know for now is that it's possible to do this if we have on Alice's side a small quantum device that can produce a small set of qubits and then send these qubits to Bob using a quantum channel. The problem is that these quantum channels are very expensive and we are far from having these. So now the open question was, is it possible to remove this quantum link between Alice and Bob? This is a quite hot topic right now, and we propose a solution which is based on universal blind quantum computing, which is a protocol made by Anne Broadbent, Joe Fitzsimons, and Elham Kashefi. And on top of that, we will add our protocol, QFactory, which is a primitive that will somehow try to simulate all the quantum computation in this universal blind quantum computing protocol. So I don't want to make you expert of UBQC, universal blind quantum computing, but I would like to give you some intuition on how it works so that you understand how we will use it later. So the idea is that we can convert any gate, any circuit in the gate model into another circuit where you replace each gate by 8 qubits that are represented in blue, and you initialize this qubit in this plus state. Then, to perform the computation, you will first entangle all of these qubits using this brickwork state, as we call it. And to perform the actual computation, you will measure each qubit using some specific angles. These angles will depend on the computation, and for each gate, you have a specific set of angles that are associated with the gate you want to perform. So we measure layer by layer, and so you first measure the first qubit using the good angle, then you measure the second qubit using a good angle, and so on. And by repeating this operation again and again, at the end you will come up with a result. So either a quantum result, if you want a quantum result, you don't measure the last layer, and if you want a classical result, you just measure the quantum layer and send, and you have the result of the computation. Now the problem of this protocol is that for now it doesn't hide anything, and if you know the angle, you know the computation. So let's try to see how we could hide the computations. Now the idea is that instead of using plus to initialize all the qubits, we will pick on Alice's side, so the one that wants to perform the computations, a qubit randomly in this set of 8 possible qubits. So these qubits are a plus state which is rotated. And so she will pick a random qubit, and then she will send this qubit to Bob. Bob will use this qubit and insert it in the graph. And by repeating this operation again and again, by picking another qubit and inserting in the graph, at the end we will come up with a full graph. And to perform the computation, instead of using the old angle that we wanted to perform, Alice will send to Bob the corrected angle that will cancel basically the rotation that she sent before. So because Bob does not know the qubit that has been inserted, he has some troubles to find the angle of measurement. So that's basically how we work. So we correct the angle, and then we do the same set of measurements as before, and Bob will send all the measurements back to Alice. Okay, so now we studied ubiquity. So the only important thing to remember is that if you have a quantum channel between Alice and Bob, you can perform blind quantum computing. And now we will replace this quantum channel by our new functionality, QFactory, that will run on Bob's site mainly, and all the communication between Alice and this ideal box will run using only purely classical communication. So here is the functionality that we want to implement. So our QFactory box will be an ideal trusted party that will pick a random theta in the set of angles that we needed in the ubiquity scheme. And then we will send this angle to Alice in a secure channel, and we will send using a quantum channel this plus theta to Bob. So this is what we would like in an ideal world, and we will try to see how we can implement this functionality in practice. So, for now, the problem that because Alice only has this classical computer and a cup of tea, she is really less powerful than Bob. So we need somehow to bring some power to Alice. And to do that, we will need some cryptographic assumption that we will provide to Alice so that she will be able to be as powerful as Bob. So we will suppose that we have a family of functions indexed by a given k, and each of these functions needs to have some property. So the first property we require is to be two regular. So it means that for any image, we have exactly two preimages in the input set. So we will call these images x and x prime. And the other property we require is that these functions needs to be one way. So if we know, this function needs to be hard to invert. So if you know the y, it should be pretty difficult to find the x and the x prime, except if you know a trapdoor. So each of these functions will have an associated trapdoor, tk. And if you know this trapdoor, basically everything is easy. You can invert this function, you can find collision, you can do whatever thing we want. But if you don't have this trapdoor, this function also needs to be collision resistant, which means that it should be hard to find two images, x and x prime, that maps to the same y. Okay, so here are the cryptographic assumptions we need, and now we will see, So these are not a crazy assumption, and we found a candidate for this function, which is based on the learning with our problems. And more specifically, we use a construction made by Michencio and Peckert that we use in a general protocol to build these functions. Okay, so now that we have this function, let's see how we can use them. So in the protocol, we have still Alice with a classical computer. So in the first step, she will produce first a trapdoor k and the associated index k. She will also pick a random set of angles. We will need later why we need them. So we will pick n-1 random angles. And we will provide to Bob all of these informations. So Bob will know only the public description. Of course, we want the trapdoor to stay on Alice's side. And we will give to Bob also the angle that we just measured. And Bob will use this information to compute these secrets. So this secret is not that complicated to understand, and we will go through it now. So the first step is that Bob will start by initializing all the qubits to the 0 state. So we have two registers, And on the first register, we will apply Hadamard to have a huge superposition on all the possible inputs. So we will have this state, and the second register will still be 0, of course. And now Bob will use the function that Alice sends before and implement it in a unitary fashion. So at the end of this step, we'll come up with a huge proposition on all the possible inputs, outputs. But because this function is chosen to be too regular, for any y, we can rewrite this expression by summing on all the possible output y. And so because this function is too regular, there are the two preimages, x and x prime, and we can rewrite it by this expression. Now, here is a time to collapse this huge state. So we will measure the second register, and because of what we just explained before, this huge state will collapse into a simple state, which is just a superposition of all the two preimages on the first register. So we'll just try to understand quickly why here we already have something interesting. So at this step, if we provide this y to Alice, she will be able to find back the two preimages x and x prime, because she knows the trapdoor. But because this function is one-way and collision resistant, we have just no way for Bob to find the two preimages x and x prime. But the prime that we need in the protocol plus theta. So let's, in this last quizzing step, we'll bring this big n qubits into just 1 qubits on the last layer by measuring all the n-1 first qubits using this set of angles. So we measure these qubits like this, and we will have some inputs, b that I will denote by bi. And at the end, it appears that it will produce a plus theta state on the last qubit. So now it's time to bring back the result to Alice. So Bob will send back the y, send back the bi's, and now Alice will try to compute this theta. So she can use this trapdoor information to find the x and x prime, and then using this formula, she will be able to find this theta. So let's stop a few seconds to understand how this formula works. So we have a sum on all the of these terms that depends on the bi, so the measurement outcomes, the alpha i's, so it's this quantity that we send to Alice, and the bits of the two preimages x and x prime. So we said before that it's hard to Bob to find these x i's. So even if he knows this quantity, because he does not know the difference here, he doesn't know if it's 0, 1, or -1, then he doesn't know how this quantity will influence this theta. So this is just to give a rough intuition of how this works. So at this step, we have a theta on Alice's side, a plus theta on Bob's side. Now, it's good, so we seem to achieve our goal, but we need to prove that this is secure. So what we prove is that this theta is a hardcore function. So what does it mean? It means that if we define this simple game where we have an adversary and we send to this adversary some random k, so the index of the function, some random y, some random alpha i's, so the angle, and some bi's, measurement angles, as a measurement result. The goal of the adversary is to produce a theta prime, which should be equal to the theta we defined one step before. So what we prove is that the best strategy for this game is to pick a random theta and just output it. From this security, so that's what in literature we call hardcore function, and from this hardcore function property we can derive proof of security in the honest but curious model. So basically, if an adversary follows the protocols and has only access to the classical registers, which is this one, then it cannot determine the theta. Why? Because we remark that because in the quantum protocol, these BRs are randomly measured by the quantum adversary. They are supposed to be also random, so we fit this model. I will go quickly through this proof. So how did we prove the hardcore function property? We basically base our proof on the Goldreich-Lewin theorems, which states that basically if you have a one-way function f, then it should be hard to distinguish this quantity from a random bit. So this quantity is just the random, the inner product between the x and a random bit string r. And to be able to distinguish it, you just have access to the r, and instead of having access to the x, you have access to f of x. So in our case, the f of x would be equivalent to the y that we measure. The r would be equivalent to this quantity that the server will know. And the secret x will correspond to this difference between x and x prime. So, of course, it's not exactly the same, but it's close enough so that we can do the proof. Okay, so to conclude, we just provide a functionality that can simulate a quantum channel using only a purely classical client. So of course, we do not have unconditional security anymore, and we need to have some cryptographic assumptions, but we are happy. We help Alice, and now Alice is as powerful as Bob. This opened the opportunity to replace quantum clients in lots of existing protocols by purely classical clients. And for now, the main downside of this protocol is the security proof that we did only in this honest but curious model. And so, of course, what we wanted to have a fully malicious adversary, and the next step will be to improve the proof of security in a fully malicious setting, and improve this security in some, improve the efficiency, sorry, in some specific application like blind quantum computing, as well as exploring new possible application. I think that this functionality can use, okay, to replace quantum clients by classical clients, but I also think that some protocols can be really improved in efficiency using this protocol if we combine Q-factory with some zero-knowledge proof. And I think that this could improve especially multi-party computations, protocols, and lots of other protocols. So to conclude, we can use this functionality to improve maybe blind delegated computing, but also maybe verifiable quantum computing, multi-party computation, quantum money, quantum signature, certified qubits, and I will let you find some other crazy application for this. So thank you for your attention, and feel free to have questions.
We have time for a couple of questions.
Thank you. Very nice. I fail to see how Q is a bit.
Which Q?
Q is Q that you obtain, that Alice can compute.
Mm.
You speak of it as if it were a bit.
So, which Q are you mentioning?
I'm sorry. Sorry about that. Yeah. I meant theta. I'm sorry. I meant theta. Theta.
Okay, so this theta is not, well, it's not a bit. It's, it needs to be chosen in the set of angles, which is 0, power over 4, 2 power 4, until 7
right.
power 4.
So it's 3 bits, actually.
Yeah, it's 3 bits, yes, exactly.
Right. And the notion of hardcore function extends to 3 bits instead of 1.
Yeah, exactly. So basically, the Goldreich-Lewin theorem claims that we have this property for a bit, but if we combine this theorem with the Vazirani theorem, we can go from a bit, hardcore bit property until a function, hardcore function.
I see. Thank you.
If there's maybe one more short question. Okay, if not, let's thank Léo again for the very nice talk.